Hello, everyone. Thank you for joining DataCon LA 2022. Welcome to the track AI, Machine Learning, and Data Science. My name is Aviva. Today, I'm your co-host. Please be mindful for our COVID regulations and keep your mask on. And also, please silence your phone during this entire session. The session is currently streaming in Zoom and will be recorded. It will be available online in a few weeks, so feel free to check it out. Today, we have our guests, Scott and Zach. Scott is the principal applied scientist from Hypergiant, and Zach is the head of AI at Andromeda 330 AI. And they will be talking about AutoDC, AutoML, and your AI development superpower. Without further ado, I'll hand this over to the speakers. Thank you for being here, Scott and Zach.
Yeah, thank you. Thank you so much.
Hey, can you guys hear me okay? All right. Because I'm going to use the microphone because I don't want to lose my voice in the end of, by the end of the day. So I'm Zach, so welcome to this talk. So Scott and I are good friends. We used to work together in the same company. We just think it will be a good idea to come here to give our some research we have done together before. So just if you go next. Yeah, so this is because I guess for me talking about the superpowers, and just in my opinion, superpowers will make things a lot easier. So I believe the tools kind of combine the combination of the tools we're going to talk about today is kind of to also become the superpower for you to develop your own AI solution. All right, and also that, so if you can go back to that a little bit, oh, it's okay. Yeah, for that, I picked that picture on purpose because for some of those limitations of the tools we're going to talk about, maybe you need some money to spend that. So that's why I actually chose that. All right, so the top outline for today is we're going to talk about maybe some of you don't know about what is the model-centric versus the data-centric AI. And the second one is to talk about the open source package we developed. And the third one is once we talk about what is AutoDC, and then we will talk about how we can combine like AutoML to develop your machine learning solution. And then we, in addition to AutoML, Scott also do some research. There's another data-centric approach you can apply to this. So we're going to show you how. And then we will have some discussion. All right. So what's model-centric AI? So traditionally, I think most of the students here, USD students, is so AI is equal to code plus data. And the model-centric AI is more like you work on the code and you keep the data fixed. And for data-centric AI approach, so once you go to the next step. So that's for you to work on the data and you actually keep the machine learning code fixed. So that's the differences. So this kind of concept is not new. It has been practiced by people in the industry for many years already. But Andrew in last year, in about March time, actually to initiate this AI, data-centric AI approach again. So that's how we're going to do to talk about this a little bit. And then if we go to next. So essentially, model-centric AI, you code some machine learning, even though for data-centric AI approach, you only need to do some auto generation. And essentially, what you need to do is to hyper-parameter tuning. So that's almost like the model-centric AI approach. And in terms of the data-centric AI approach, the definition is actually you would systematically engineering the data used to build the AI model. And then we have some examples here. So those are kind of Tarlow and HyperOp, they are open source, a tool you can use for you to do hyperparameter tuning. And in terms of for AI-centric approach, we currently don't have a lot, but we do consider vision engineering as one of the data-centric approach, and we have some open source package called Arrow and feature tools, and also small we consider that to be some of the data-centric tools you can facilitate. And yeah, you can think on that. So why we want to go with the data-centric AI approach? So based on my career in the last 10 years, so we have been building different machine learning models, and you do use the model-centric approach. And so, for example, if I have a model and to classify new docs and paths, that's the computer vision. And then if you, so for model-centric AI approach, you most likely have some incremental improvement for your model. For example, if you have the 85% accuracy for model-centric AI, pretty much fine-tuning your hyperparameter, you can get 2% more. But for data-centric approach, because you try to improve the data, and actually your data quality for the training is a lot better. So in that way, you can, in a lot of cases, you improve more than 10%. So I've been working on it as a data scientist for many years, and I've seen this firsthand. So for the next, so there are some tools also available in the market right now for model-centric approach. You use a lot of different AutoML solutions provided by Google or Amazon. So they all have their own AutoML tool. And so the good thing about AutoML is you don't need to write a lot of code actually to do hyperparameter tuning. You can actually just put the data, and then you have the model done it, and you find the best solution for you. So last year, in around December time, we actually built another open source tool called AutoDC. And slide. Yeah, so we built AutoDC. It's called automated data-centric processing. It's similar to AutoML. So in the model-centric AI approach, if you use AutoML, you would just need to, the only thing you need to bring is your input data, and then you put in AutoML, and you would do almost for you like data processing, vision engineering, and also generate model for you and do some parameter tuning. And then the model would do the output. So we have similar idea to do AutoDC is actually to provide this automated way to process your data. So the only thing you need to bring is actually some label data set, and then you put into our AutoDC toolbox. We would have we'll do these three things for you. The first thing is label correction, and then the second thing is to give you select some edge cases for the data, and then we do the documentation. And then once you put in your label data set into our AutoDC processing, and then you will spin up the improved data set. So actually, you don't need to do any processing with AutoDC. So that's the similar idea with AutoML. So this is some details of the AutoDC workflow. So the first thing you need to do is to bring the label data set, and then AutoDC will. So this is more like the detailed view. So the first step, so currently we only support computer vision, so we only test this with image data. So the first thing we would create some embeddings using ResNet 50, and then we also do outlier detection. So we utilize isolation forest, so that will detect outliers for you. And then because those data are most likely outliers for different edge cases, and then you might have some incorrect labels in those cases. So that's how we kind of provide a solution for you to actually track your label in that stage. And then once you do the label correction, the next step is we have some, so you need to kind of find another parameter here. So which I'm going to talk about later is you need to select some edge cases, and then we do classification, you add more of those cases in the data. And then the dataset is actually work out improved data. So there are some limitations in this approach because when you fine tune your data, you still need to put into a pre-selected machine learning algorithm. So for that, we are not able to do that for you at this point. But also, I will talk about some limitations more later. So this is one of the examples. So the data set here, say it's a handwriting Roman numbers. And then, so one of the AutoDC processing is to help you to generate some embeddings. And then, if you can go to the next slide. And so for the figure A, that's the actual embeddings. And the figure B is we put the actual image in each point. And then the figure C, which it's actually the outliers. So you can see we generate this nice cluster. And then around that cluster, we can find different edge cases and outliers. And if you go to next, you can see actually that red box will give you that is the round label. Because for this data set, we have number 1 to 10, and those are the number 1 class in this data. And then using this approach, we'll help you to identify so this around table. Oh, okay.
Yes, come here.
Oh, I forgot we're gonna show the video. All right. Yeah, so this is our AutoDC starter example. So actually, our tool set is open source, so you can actually see. Go to our GitHub. I cannot provide the URL, but yeah. So we are continuing developing this tool and to help data scientists and even data analysts to make their data quality better. And so this is one of the starter notebook. So we put this in the notebook and we build a different function for you to use. But if you just, the only thing you need to bring is the data. You can just specify the path to your data set, and then you will be able to also fine tune this parameter, and you can just run all each processing, and you don't need to do a lot of coding. So we are hoping to add the easy to use UI in the future. So you don't need to do actually coding. Yeah, so that's the end goal. All right. Okay, so that's that. So next, I'm going to talk about some examples we did to use AutoDC actually to improve your data set. So we test on 3 different data sets. So the first one is Roman numbers. That's the handwriting one, and we have about 3,000 images with 10 classes. And the second data set that we tested before is dogs versus cats. So that data set got more images. It's 25,000 images. They only have 2 classes. And the third one is coming from Stanford University. There's some snails image data set, and we have 4 classes for that, and only about 5,000 images. So we select those data set on purpose because we want to test AutoDC in different type of data from like 2 classes to 10 classes, and also a couple thousand to maybe 25,000 images. So we can test the capability of the our framework. Okay, so this is the AutoDC improvement. So right now we only support image classification, but you have, so right now the green bar show is modified data, which will be the original data set. And then once you put that data into our AutoDC, it automatically correct the labels and also improve the data set quality. And then this will be the improved data set accuracy. So you can see in each data set example, you can see that we improve the accuracy about 10 to 15%. And you don't need to actually manually go through your image data and to see which one is not the right label. And you don't need to go through that to generate the new data set for yourself. So yeah, so this is really easy to use. You just need to put in to our framework. And also in terms of the time, this is approximately, we try to estimate this. So actually, we had the intern actually to try to do this and onto the time himself and how much time he would need to manually process in this type of data. So with our AutoDC solution, so we significantly reduce the time you need. For the Roman numbers, the intern would take about 4 hours to improve up to the same quality of that data. And for the cats and dogs, it would take 9 hours because you have 25,000 images. It was kind of fun for him to do in the beginning to look at different dogs and cats images, but in the end, it's just a pain for him. For the third one, it's it take about 6 hours. So it's around 80% of the time will be saved. You don't need to go through that manually. All right, and then so once we have done that and we realize there are some limitations in this framework because we still have some parameter you have to tune in AutoDC. And so that one you have to manually try different one. Since we have the small data set, so each process will run maybe a couple minutes. So it's not too bad for now if you try to fine tune that the parameter in AutoDC. And the second one is you still need to identify the training model in advance, which means for the image data, you most likely will use Resident 50, or maybe you have a VisionNet with another option. Anyway, you have to select that in advance, so we don't provide that for now. Yeah, so those are the limitations. So that's why we want to kind of put AutoML into the picture actually to fill this gap. So there are two different ways you can combine AutoDC with AutoML. So this is the first way you can actually use them separately. So you have the input data put into your the AutoDC, and then you got the input data set, and then you just put into another AutoML algorithm, and then you do this iteratively to the end. You can improve the your machine learning model and your data at the same time. And this is the second way you can do. Is I think this is the better way, but we haven't developed most of the components in this yet. Which means we're gonna have to fine tune AutoDC as one of the AutoML parameter. So for this, you probably need another open source kind of AutoML, so we can actually implement this and also integrate them together. So this is more ideal way. We haven't completed this work yet, but I'm going to show you if for the first approach, what kind of improvement you can get. So as expected, if you use AutoML plus AutoDC, you can actually improve your model accuracy even further from, it's additional 2 to 5% increase if you use AutoML plus AutoDC, which means this way you don't need to do actually any coding. Just need to put your data into this framework, and it will screen out and give you the increase of the accuracy. Oh, so just also to mention, AutoML run, it's from like 8 hours to 20 hours. So another limitation is it takes time. But if you want, after maybe 12 hours, and you during that time, you can run the processing during the night when you sleep, and when you wake up, you can actually get a really good machine learning model for your application. Okay. Yeah, so the second approach is still under development. We're going to share that soon once we develop that part. So that will be our future work. And we expect that to be more time efficient. So right now, we still have a lot of manual processing, but in the future, it's all being will be automated. Okay, all right. So.
Thanks, Zach. So one thing I wanted to do was kind of connect the dots on how you would apply this to like the work that Zach just showed is what I would say like our academic research, but we do use these type of tools on actual client work, and we do that by throwing this stuff into AutoML. So traditional machine learning and AutoML pipelines they select the pre-processing algorithms and the feature engineering algorithms and do the model selections, and they do them all in silos. Well, our AutoML approach is a bit different, where we actually score all of our pre-processing and feature engineering and model selection tasks as one, like giant optimization framework. So, we're developing an open source package to do this. And so I'll show some of the results of that. But, we have used this stuff on client work, and if it should also give you ideas that there are many open source libraries which you can build on, like our AutoML algorithm actually is built on Optuna, which is an open source optimization library. So you can imagine that you might want to do some preventative maintenance problems. So here what I have is a data set from an aircraft engine and a bunch of data from sensors. And when you, if any of you guys have ever fused data from a bunch of different sensors from aircraft or any sort of IoT device, you know that you get missing values because different sensors populate the data on different time frames and such. And also you get weirdly behaving sensors, like maybe you have a low cardinality sensor that just behaves in like stepwise function or something like that. And so how you actually generate new features and fill in missing data and clean that up and decide what's an outlier is, I would say, a complex process. And instead of like figuring that out, we just suggest to actually just, figure out all the possibilities for it and then run them as pipelines. One result we get from this approach, so here we're actually solving an imbalanced classification problem to predict when we need to replace that engine. And on the x-axis, you see encoding. So we have either drop variables that need to be encoded or one-hot encode. So one-hot encoding is like a very common feature engineering technique where you just essentially encode the labeled data as a binary variable. And then on the y-axis, you have a dropout rate. And dropout rate is a neural network parameter that introduces bias into your model. So we have on the x-axis, a parameter that introduces complexity in your model, and a y-axis that the higher it is, it introduces bias to your model. And so what we can see is that, what this tells us is that there are models that give us lowest loss. So you want your loss number to be low in this case, that just drop those features and have a really low dropout. So it says, don't actually add any more features to the data set and just have your model not have a lot of dropout. And so this gives you, by running our AutoML, this gives you like an intuitive decision on, how you might actually model this process instead of, in a silo, encoding the variables and then hyperparameter tuning the dropout rate itself. Another thing that you can do is you can, get these hyperparameter importance plots. And so one thing you might look at is that we have a random state variable and an encoding variable, and you notice that the random state of the model is more important than or the learning rate or the dropout rate. So that might tell you that the actual those actual variables are actually not that important to modeling at all. It should tell you that, oh, well, if it's not more important than actually selecting which random state, perhaps I should focus on tuning the other variables, which are weight decay and data scaling. So previously what we've had is these complex AutoML systems that do these data-centric processes and then picks the best model. But now we also get insight into how the models are making, finding the best models, and also like what kind of data-centric processes and hyperparameters we want to model itself. Do you want to? Yeah, that's all I got.
Yeah, so Scott just talked about different data type is the tabular data. So I just wanted to show actually we have for data-centric approaches, not only for image data, but also kind of for natural language processing or a different tabular data set. So just show different examples, you can try that. So this for the discussion is, so the first one is with we designed AutoML framework to be more modular and flexible. So that could be also updated if we have new technique to do outlier detection better. So we actually update that in the framework. And also AutoDC now can not only be used in the machine learning development stage, but it could be also used in once your model is put into production. You can use that AutoDC framework to ensure the quality of your data in the production environment. So that's the first one. And the second one is we just show if you use AutoDC plus AutoML, and also with the second one that Scott just shared is to use a data-centric approach plus AutoML that will actually automate a lot of your menu processing in your machine learning development work. So we just to show that if you try this too, and you would get a better model, and also a lot of the process can be automated, would save you time. Yeah, so that's something we are go with. And the third one is we designed this for more for low code and no code ML solution for domain expert, because a lot of I work in the battery company before. And a lot of them, they are just research scientists. They don't know how to coding machine learning, but they are expert in their domain. And if we can provide this low code and no code solution for them, so anyone can do machine learning. So that's also our goal. So the only hard requirement is you did require some compute resources, because this processing would take time and also take some money. Yeah, so that's why I showed the first slide, just to maybe you need to be reached, but yeah. So right now we don't. So a lot of the cloud providers, they provide different credits for students, and also the compute resources, especially GPU, become cheaper and cheaper, and also more accessible for people. And so that's yeah, so it's really good one to have. So hopefully this won't be any limitations in the future. Yeah, we also want to call for like different people who can help us to develop further develop this open source solution. And so this is the link. And so if you have any that would like to contribute to our code base, yes, feel free to contact me for that. And yeah, because we still have a lot of things to do. Yeah, I just want to talk about what sponsors. And so the Scott is it's working for Hypergiant. They are doing a lot of data science services. And my company, Andromeda 360, we build an open modular machine learning platform. And we also build something called StarPack for you to deploy your model just within a couple minutes. Yeah, so feel free to visit our website. And so our AutoDC solution will be previewed on our platform as well. So if you want to try with using our platform for your model development and also model deployment, yeah, feel free to contact me, because we are doing a community environment. I mean, the community edition now, so you can actually use our platform for free, just for a couple of weeks. I guess that's. Do you want to add anything? Okay, I think that's all I have.
You were showing the parameter importance. How is that determined?
Yeah. So the back end of this is a database. So we run our AutoML, and it does a bunch of experiments, and it stores all the experimental results in a database. And then we're able to train a random forest on top of that. So each of the hyperparameters are features in that problem, and then the target is the actual loss, and the random forest tries to predict which parameters gets you the best loss. So kind of one of the advantages of any sort of like optimization tool like Optuna, or as like really popular like weights and biases or something like that, is that they store all of your hyperparameters for you, and you can kind of do experimentations on top of that. Does that make sense?
Yeah, and then when you were showing the like 18 to 20 hours of the whole process, is that incorporating that?
So yeah, so that was the entire AutoDC and AutoML process. What I say is like, depending on the data type, it will take longer or shorter, right? Like even I don't know if you've ever like passed images through like ResNet 50 or something like that, but like that can take a long time if it's like on, you know, a million images even.
But the idea is by the time you pass it to one of that first, you already have your parameters figured out.
Exactly.
Thank you. Are you using regular way to interact with features or?
Oh yeah, for the feature engineering, we're this particular, this is actually scikit-learn's one hot encoder, or Panda's one hot encoder, I think. And no, it's scikit-learn's one hot encoder, but some open source. And essentially, what happens is Optuna, it gets the the result, right, and it says, oh, perform that action, and then it performs that action and changes the data set. It's traditional machine learning pipeline. We're just recording stuff, to be honest, and reporting those results. Like another motivation of this is like you want to deploy less complex models. The more features you have in your data set, the more monitoring you have to do.
AutoML part, are you doing architecture search or model?
Yeah, so we have a fixed model. It's a big neural network, and we're pruning and regularizing. So what Optuna is actually doing is searching over a bunch of different regularization techniques and a bunch of different pruning techniques. And so it starts with like a really complex overfitting model, and it slowly shrinks down into the model of the appropriate size. Yeah, it starts off as a 9-layer MLP, actually, and then it just shrinks down.
I'll be just louder. So if there's any versioning on the models, then how do you manage the model deployment?
That's a good question. I will. Do you want to talk about StarPack or?
Yeah, sure.
Mhm.
So so your question is how do we do a deployment, right?
Yeah, how do you manage the deployment and rolling back for your models if there's any versioning on the models, so on, so on, so forth.
Yeah, so in our company, actually, we developed something called StarPack. It's the similar to if you used Terraform before, but Terraform is to manage your Kubernetes cluster. We use a similar way to manage the model deployment. And so within our platform, so if you build a machine learning model, and we would help you to manage the different version you have. And then so once the model is ready to deploy, you can choose which one you're going to deploy, because we track different version for you on the platform. So once you selected maybe something we call best round, so you will compare which model perform will be the best, which maybe you want to select the model has the lowest loss. And then once you put the model into production, we just actually put your model into a Docker image. And then from that Docker image, you deploy into Kubernetes cluster, and that will become the cloud endpoint. And then if you want to roll back to the previous version, you can actually go back and to change the version, maybe version 2, it's a version 1. And then you update that model, and then you push your model into a Docker container again. You can also make that Docker container become the cloud endpoint. So that one, yeah, so that's how we manage that for different versions of the model within our platform. That answers the question.
Yeah, and I mean, the other thing you can do is just associate like an experiment with the model artifacts that you're, so these deploy all the model artifacts that you would need to reproduce the pipeline. And as long as you have that experiment with the model artifact, you can use whatever like deployment system you want.
My question is around like
I'm sorry, what was how is it different than what approach?
So like the transfer learning and future learning, they are connected using less amount of data in future applications. So how that approach
Yeah. So just to reiterate the question is, how is this approach different than using like transfer learning or few shot learning? Well, I would say that transfer learning and few shot learning is probably part of a data-centric approach. For example, you can imagine using like, BERT or another pre-trained NLP model to generate features and use that. The difference is that we're trying to evaluate whether doing that is actually useful or not for a downstream task. Whereas transfer learning is just the process of transferring pre-trained or pre-learned knowledge to a new problem. We're trying to figure out if that is even useful or not as part of a full modeling pipeline. Anything to add?
So in terms of the AutoDC toolbox we built, so you can actually so once you got the improved data set from AutoDC, you can put into transfer learning as well, because we actually use transfer learning to improve the model. Yeah, so they can be served as a separated process, but I think they are pretty much a similar idea, is to improve the data in some sense.
Yeah.
On the DC learning, on the AutoDC, so it finds outliers. What does it do after?
Oh yeah. So once you found the outliers, you will have user to decide how many outliers are incorrect labels, and also how many of those outliers are actual edge cases. So edge cases is a bit different from different from your normal distribution of your training set. We want to find those outliers and yeah. So one of the process. Let me see if I can show that. Hopefully, it's not too small to show. But yeah, so once you identify the outliers, you will go through the label correction, and once you correct the labels, and it would prompt you to try to define how many edge cases you want to put into the new data set. And then we would use data augmentation to generate the data set, more like a fake data set from those edge cases, to add more back to the data set. So actually, so in this example, I remember if we have 3,000 images as a training set, and then when it come out, it would correct your round labels and also add maybe 500 more images to your dataset. So your dataset will have more balance. It would cover the normal dataset you have, and also added some edge cases. So in that, we kind of prove that the model actually will generalize better that way.
So it gives you a chance to find the wrong labels and the upsample edge cases.
Mm-hmm. Yeah, that's right. Mm-hmm. Yeah, we actually will generate the actual images. Yeah. Oh yeah, so that's kind of user defined. You can define if you want to rotate the image, or maybe flip the image, or to change the focus. I forgot which one. Maybe to blur the image. So in this one, we actually just implement the Keras data generator. So anything in Keras you can do it here.
It is flexible enough if you wanted to like use some sort of GAN or like, variation, like some sort of generative model to actually generate that data. But kind of the illustration is we're doing these simple things and getting like great performance improvements. So I would like a little bit caution because like training again is an expensive process in itself, right? Yeah.
Thank you. This is the end of our session. Thank you for your time. Thank you for your questions. We will end this session now. It's time for lunch. Lunch, there's a lot of restaurants. If you have any questions about how to take care of